Let's get started with the second talk of this morning. It's a real pleasure to have David Oxtoby, the president of Pomona College, as our next speaker. David was educated in chemistry at Harvard and Berkeley before joining the University of Chicago faculty in 1977, where he became a full professor in the mid-'80s and dean of the Division of Physical Science after that, before moving to his current position in 2003. During that academic progression in 1980, he was a Camille and Henry Dreyfus teacher scholar. Somewhat coincidentally, I think, the same year that Marianne and I were accorded the same honor. So it's a pleasure to have David here to talk about climate change.
Thanks so much, Matt. And I'm actually going to do something a little bit different. I'm going to say a little bit about climate change, but for the most part, I'm going to use that as a theme to talk rather autobiographically and personally about careers, because I thought that would be interesting for many of you. Now, of course, climate change is a subject I am passionately interested in. I could have given an entire talk on that. It certainly is one of the defining issues of this coming century for chemistry and for many other fields as well. If I'd given that talk, which I'm not going to, it would have included a lot of information that I hope you all know, although unfortunately much of the general public does not know about the reality of climate change. So I'm just going to give you a couple of tidbits on climate change, which are interesting things which I've used in various public talks myself, which you may not be aware of. One of them is the observation that you can think of climate change in terms of a speed or velocity at each point on the Earth's surface. Now, it's fairly natural to think about isotherms, let's say. Where is a given isotherm over time? So now think about how that isotherm moves with time, okay? If climate is getting warmer at any given point in space, then if you move at, let's say, a constant temperature isotherm, you are moving at a certain speed. Now, do you have any guesses about what that speed might be, order of magnitude? How fast does climate change take place in terms of a speed moving along the Earth's surface? Just a rough order of magnitude you would estimate. Okay, it's 10 miles a year, a little slower than that, actually. Some of the faster regions, it's not, of course, not the same everywhere across the Earth's surface, but some of the faster speeds are on the order of 1 kilometer a year, 1 kilometer a year. So, for example, a study looking at California, an area in the Central Valley, was identified as roughly 1 kilometer per year, okay? Now, I just find that useful because you can think of, suppose you're a farmer, okay? Well, are you going to move your farm 1 kilometer per year? That's sort of difficult to do. Suppose you're a plant or an animal, okay? Maybe you can move with the climate, or maybe you will run up against a change in topography and you won't be able to keep moving. So the idea that climate change causes these isotemperature or isoclimate lines to move with time, to me gave a different way of thinking about climate change, a very visual way, which I like to use when I talk. Another thing is, of course, these velocities may be pointing downhill or they may be pointing uphill, okay? If you're in a mountainous region, the velocities might be pointing uphill, and so what does that mean for the constant climate line to be moving uphill? It means that eventually you get to the top of whatever mountain you're on and you run out of climate space, okay? You run out of space for whatever species you have, okay? So that was sort of an interesting observation about climate change that I found useful. So it's one of the little tidbits I'd like to share with you today. The second thing is a little bit different. It involves psychology and the way in which people answer questions and the way they think about things. Of course, as scientists, what we try to do is assemble evidence. We come to conclusions. We hope that those conclusions are firm, that they won't change with time unless new evidence is presented. That's the whole idea. That's the way science works. But I'm not sure many of you are aware of the role of studies that have shown psychology in the general public and how general public reacts to an issue like climate change. For example, there was one really interesting study that asked people, do you believe that climate change is real and is it caused by human activity? And they found that the answers people gave depended on whether the last few days were warmer than average or cooler than average, okay? And quite dramatically in terms of the level of belief in is climate change real depended on, oh, it feels hot today, therefore climate change is real. And so you imagine what that does in Washington, D.C. and so forth in terms of policy. There's an even more dramatic experiment where people were asked the same type of question, and depending on the temperature in the room, okay, which is totally artificial, they answered differently, okay? So if the room felt warm because the air conditioning wasn't working very well, then people tended to believe more in climate change than if the room was cool. So I just say this because we're up against an awful lot in talking about this issue. We have huge scientific issues, really interesting, important work for chemists and others to do in this area, and I hope that many of you, I know some of you work in this area, and I hope that many of you think about this and work on it in the future. But we also have huge issues of public policy, of ways of conveying science to the public, which are equally challenging, if not more so, okay? So I just like to begin with that very brief few comments about climate change. So for those of you who are expecting a full talk on climate change, those are two little pieces. I'm happy to talk with you further at another point, but I just would like instead, rather than giving a scientific talk, and you're going to see I'm not going to use technology at all, I'm just going to talk, and rather than even give a public interest talk, which I have done quite a bit of on the subject of climate change, instead of that, what I'm going to do is talk personally about my role as a teacher scholar and how it's shaped my career, and climate change is going to keep coming in and out. It's going to be a recurrent theme through my talk. So I hope that each of you will take not specific suggestions which I'm making, but broad inferences from the comments which I make, as you, those of you who are newly appointed teacher scholars, as you think about your own careers going forward. So as Matt mentioned, I was named a Camille and Henry Dreyfus teacher scholar in 1980. At that time, there was a single program. Now the program is the Camille Dreyfus and the Henry Dreyfus, two different programs, ones at PhD institutions and undergraduate institutions. But the key observation I would make is that both of these awards, now the Henry and Camille Dreyfus Awards, and the original award that I held, were ones that connected scholarship with teaching. So they had set high expectations for research, but they also set high expectations for teaching. And that to me is extremely important. It's an important message that needs to be out there in our colleges and universities and in the country, because too often research and teaching are held up as in opposition to each other. You do one well, you must be somehow slighting the other. How do you combine the two? My experience over a career which started, of course, as a faculty member, and then I became a dean, and then president now. I was first at, as Matt mentioned, an R1 university, University of Chicago, now at Pomona College, an undergraduate college, is that I found that in almost all cases, the really fine teachers also are the fine researchers. And there's some really good examples right here in the room. When I look around, people like Dick Zare and Mary Ann and so forth, there's some great people who are amazing researchers, but also who clearly have stood out for their commitment to teaching in many dimensions as well. So the skills that go into good teaching, these include obviously passion for the subject, but also ability to explain your subject clearly and effectively to many audiences. Exactly those skills in teaching will be tremendously beneficial for the research that all of you do. So I guess the first message which I would like to share with you is the importance of connecting these two in your own careers and as you think about your own plans going forward. They are really vitally connected to each other. That's the whole idea of the academy, is that at the same time we are pushing forward the frontiers of knowledge, advancing research and science, we are also conveying that to students at all different levels, graduate students certainly, but also students who are just entering the field, who are being inspired by the work that you are sharing with them. So to me, that is a really important observation to make. Now, when I started at the University of Chicago in the 1970s, I, of course, jumped right in, started a research group. That was a very high priority to bring in some graduate students to get grants, of course, to support my research. I was working in theoretical physical chemistry and specifically liquid state dynamics, light scattering, areas like that. And so I jumped right in with a research group. And there was a tradition at Chicago to try to protect untenured faculty from elementary teaching. And so basically we were told at the time, sure, teach advanced courses. I taught my advanced statistical mechanics course and see at least one person in the room who was in that class. And so from there, I sort of started at that level, and it was a good way to start teaching, of course, because it was a subject very, very familiar to me. But I'd always been interested in teaching, and so when I was offered the chance as an untenured faculty member to teach general chemistry, I said sure, even though I could have said no, wait till after I've gotten everything set and I'm ready to do it sometime in the future. But I taught general chemistry. And as usual, when you do something and I used a great book by Bruce Mahan, whom I had actually taken a class with and studied with at Berkeley when I was a graduate student there. So a classic general chemistry book. But whenever you do that, you always say, oh, I would like to do it a little bit differently. If I'd like to explain this subject in a somewhat different way and so forth. I mean, Mahan's book was a fine book to work with, but you always get ideas of how you might do things a little bit differently. So I had talked, as I went into this general chemistry course, talked quite extensively with one of my senior colleagues, Norman Oxtoby, and Norman had taught general chemistry for many years, and so we talked about how to teach the course, about Mahan's book, and so forth. And so we made the rash decision that we could do better. We could write a book of our own, and so I got started as a junior faculty member, which probably was a little bit crazy, to begin thinking and working on a general chemistry textbook. So that book has gone into multiple editions since then. So I started as an untenured faculty member. We actually delivered the full draft of the manuscript just 2 years after I got tenure. And it was incidentally a week after our second child was born. So it was sort of a competition which would happen first, get the book finished or our son being born. It was an amazingly busy and challenging time. Research was going well, but I was also really excited by the teaching and the textbook, giving me a different way of thinking about teaching chemistry. Another thing that happened as an untenured faculty member was that three of us, myself, a physical chemist, an organic chemist, and an inorganic chemist, all of us untenured, we got together and said, we don't really like the curriculum. We think we should change it. So we were sort of young Turks rebelling against the way it had always been done. And so we came up with, let's change things in this way. Let's get students maybe doing some organic chemistry a little bit earlier on and moving some things around. Now, not everything that we proposed as a young group of faculty members in our department actually was adopted, but our senior colleagues did actually listen to us, and we did make some changes in the curriculum. And then the last thing to mention is that each of the three of us was eventually promoted to tenure. So it was something that we felt we took some chances, got involved in some things that might have been a little bit off the usual course, and the final results were positive in that direction as well. So at the same time that I was advancing my research career and, of course, receiving grants and so forth, I was jumping into teaching-related areas, curriculum, thinking about writing a book and so forth. So I'd also encourage all of you, don't just postpone thinking about teaching to sometime in the distant future. Get involved now. Think about what you can do now at these stages in your careers. Research and teaching can go back and forth. You can emphasize one for a few years, emphasize another for a few years, and that's a great way to work through a very exciting career. And in fact, we those of us in the academy have that special opportunity of sabbaticals where we can do exactly that. And that happened to me at several different occasions where I got, let's say, pretty heavily involved in a teaching type of area focus, and then with the sabbatical I moved for a full year completely into research and moved in a different direction. So that's something which you can do as well. So I'd like to actually mention one of my sabbaticals which had a direct and also serendipitous effect on my own career, and that was in 1987 to 88 when I spent a year at the University of Bristol in the United Kingdom with Bob Evans. And my research until that time had focused on light scattering and theory of liquid state dynamics and relaxation in liquids. But I moved in a new direction toward the development of a new microscopic theory of nucleation. So phase transitions and nucleation, and that theory was based on density functional methods in statistical mechanics. So it was a new direction for me. and it actually shaped a lot of my research over the next 15 years. So it was wonderful to have a sabbatical, to learn about some new areas, to actually sit down and do programming and calculations myself instead of just supervising research students and postdocs. So it was a wonderful and productive sabbatical. But one of the things that that new direction did was that it led me toward atmospheric chemistry, because I was working on fundamentals of nucleation, very simple, basic spherical molecules, very crude approximations from a theoretical point of view. But I started attending meetings on atmospheric aerosols and nucleation. And so getting into the atmospheric chemistry community, realizing there was an awful lot of very interesting, quite far from my own research going on in atmospheric chemistry. But that was the beginning of learning about the role of aerosols in greenhouse warming and climate change and so forth. So my research direction shifted me in a direction that ultimately connected to some very important areas related to climate change. Now, another thing that happened during that sabbatical year was that I had an invitation to take part in a conference. I was in England, but this was a conference in Colorado, which brought together 50 chemists who studied liquids in various ways, with an equal number of scientists involved in ocean science. Okay? Now, here I am, a chemist, and I'm on the extreme edge of theoretical, every molecule is spherical, et cetera, and here we're supposed to study water and the oceans, not just water, pure water, but water in the oceans and all of the problems of ocean science. So it was quite fascinating for me to work and talk with a bunch of scientists, some of whom had huge practical knowledge, some of whom were very much more on the theoretical side, but about some real issues in ocean science. And so that type of opportunity, just to be able to take part in that conversation, to hear about issues that I hadn't heard about, was an amazing opportunity. So if you have that chance to get to a very interdisciplinary conference where there's going to be people from completely different areas and where there will be a lot of discussion, not just sitting and listening to talks, which this conference was exactly that, a lot of wonderful discussion, do take advantage of it. There was a keynote talk at that conference by Ralph Cicerone, and Ralph, of course, is an atmospheric chemist. And what he told us at the conference, he talked a bit about the emerging progress on the chemistry of ozone and the ozone hole, and ways in which the problem had been recognized and steps were beginning to be taken to deal with that problem. But then he also spoke in his talk about the next big challenge, and the fact that it is much bigger and much harder to deal with, namely greenhouse warming and climate change. So this was in the late 80s, when this wasn't in the newspaper all the time. I had known about the issue. In my chemistry textbook, there was a section about greenhouse warming, but it wasn't something that really had struck me as this is going to be a defining issue for the environment for the next century. And so Ralph's talk really showed me that and made me, pushed me in some new directions, hearing that talk and realizing the importance of the issue. So it caused me, first of all, to get into some of the science at a deeper level, science behind climate change, understanding how those issues all worked. So there were two effects that this had in terms of my career. The first was in changing my teaching. Now, I changed my teaching for two reasons. One is that, as I've mentioned, I had already written a chemistry textbook, and I did assign it to my students to buy it for however much absurd amount of money they charge for textbooks these days. And so in the past, I might have just marched through the textbook, and today is lecture 6. I'm going to be talking about material in sections 3.4 and 3.5 or whatever. But when you've already written the book and you've explained everything as clearly as you can, if you just go to class and say, okay, now I'm going to do exactly what you should have already read in your book, that's not really very effective. And so it caused me to begin to rethink how to teach a general chemistry course. The second reason for changing this was my interest in environmental issues, stimulated in part by the climate change issue. And so, and I was also trying to interest students in chemistry, and getting students interested in chemistry is not just now we're going to move through this topic and so forth as it is laid out in the book. Their interest usually comes from real issues, real world issues, whether it's they want to be doctors and they're thinking about medicine, or environment. And so what I did was I really turned my course around and changed the whole course so it was built around the environment. So I would begin with a opening topic, which might be, let's say, greenhouse warming, and develop the chemistry for that as I went along. So I would be assigning sections of the book that were relevant to that particular topic. And it's amazing, you can actually teach essentially all of general chemistry, bringing it from the point of view of environmental issues. So it refreshed my teaching. It made me really energized about getting into the classroom when I'd written the book. And it also, I hope, helped students to appreciate that the chemistry they were learning was deeply connected to some really important issues. And I continue teaching. I teach an environmental chemistry course now on atmospheric chemistry. And of course, it is, as you would expect, built around specific issues in environment. We always begin by talking about smog, and a topic familiar in Southern California, although less of an issue now than it used to be. We talk about ozone, and then we spend a lot of time talking about greenhouse warming and climate change. So connecting the chemistry, the basic chemistry, to the environmental issues is something that I really enjoyed doing. I also took part at that time in the early 1990s in a coalition, and there's at least one person I just saw earlier who was involved in that, the ChemLinks Coalition, which was a coalition of 2 research universities and a dozen or so Midwestern colleges that were developing materials around environmental issues for use in chemistry courses. And so Washington University, St. Louis, the University of Chicago, and a group of Midwestern colleges. And so to me, that was also a great experience to work with colleagues from different types of institutions, universities and undergraduate colleges, with a very close partnership in developing some great teaching materials that I could then use in my course in environmental chemistry. So that was a good step forward in the 1990s. Now, I also started to talk publicly about the issue of climate change, and so I gave talks that moved from my core area of research, nucleation and aerosols, to broad issues of climate change. And here's something where, again, let me just give you some advice. We are all afraid to talk about something that we are not specifically an expert on. And so there's a tendency always in talks to say, I really know this, I know this down pat, this is what I'm going to focus on, and so we give pretty narrow talks. But if you're going to talk to the public, you have to talk about things where, frankly, you are not particularly an expert. Hopefully you're more an expert than your audience, but you have to be willing to take those chances because that's the way you're going to connect to big issues. And so when I talk about climate change, sure, but part of it is aerosols, which I do know something about. A lot of it, though, involves physics, chemistry, economics, you name it, fields that I'm not an expert in, but I've learned enough about that I can try to bring them into my talks and make them interesting. So I became Dean of Physical Sciences at that point, and was doing quite a bit of traveling around and fundraising and things that deans do. And I would give talks in which I would talk a little bit about the University of Chicago and why people should give money to the University of Chicago, but I'd also bring my science in. I'd talk about climate change, and I can still remember a talk to a group in Dallas that included some people in the oil industry who were very skeptical. This was in the mid-90s, didn't believe any of this. They probably still don't believe any of this, but in any case, it was a really great way to engage, to show myself as a scientist talking about an issue of significant public importance. And those talks I continue. I'm president now at Pomona College and spend a lot of my time on the road fundraising. But for example, next month in Washington, D.C., we're going to have an event where we have several faculty giving talks about their areas of specialization, and I'll be giving a talk on climate change to that group. So these people there will see me not just as a president, but also as a chemist who's interested in about a very important issue. So in terms of you and your plans, I hope that you will also take advantage of chances to talk about issues of public importance and public interest. Go beyond your specialties. It might involve just talking at a school. If those of you who have children, your schools would love to have you there to talk to school children, high school all the way down to elementary. I did some of that earlier on. Or if there is a local Rotary Club or some group that they're always interested in having people talk. And you have to take a step from your own area of research out to a broad issue that it connects to, obviously, but think about ways in which you can communicate the science to the public, because that's one of the most important things that scientists need to do. Think about writing an op-ed and so forth. There's many ways in which you can help show that science is not just something that happens behind closed doors in laboratories, but it connects to real-world problems, and it connects to the interests and passions of the rest of the country and the rest of the world. Now, the last thing I want to say a few words about is another way in which, another type of service to colleges and universities that employ all of you. Now, service is often the third component. That there's, of course, research, which is wonderful. It's why we all went into science. There's teaching, which I hope all of you, I assume all of you have become passionate about and are involved with as well. And then service is that ugly thing that you have to do, and you say, okay, I did my service. I served my term, as if you're serving time in jail or something like that. Service is often thought of as a boring, annoying obligation. You have to be on certain numbers of committees, and so you can check that off and say you did your service. And it's something, when we look at tenure and promotion, service is that sort of third category that helps a little bit, but is not really rated in the way that research and teaching are. So it's something you do because everyone else does it, and you have to do your share of it. I wish we could think of this a little bit differently, and I read an article a year or so ago by Kathy Davidson, who is a humanities professor at Duke University, where she's talked about, why don't we change the language, just the way we talk about it, from service to leadership. And leadership doesn't just mean being department chair or dean or whatever, although that might be one component. For some of you it will be, obviously, in the future. But there's leadership also just in other ways in which you're involved with your institutions, and whether you're serving on an important committee. If you step up as a leader by making some important suggestions or making some changes, that's leadership. And developing skills of leadership are one of the things that colleges and universities need to do. Because the leadership in academia generally comes from academia. We don't go off and hire someone who's been a great leader in some business. It occasionally happens, but you develop leadership skills through the academy. And so I would encourage you to take advantage of those opportunities as well. And everyone can be a leader in some area, even if not every leadership role is appropriate for each of you. So in my own case, I was an associate dean in the 1980s, thinking a lot about undergraduate curriculum. That's one of the areas I got connected beyond chemistry to all of the physical sciences and mathematics, thinking about undergraduate education. Then I became, on the research side, director of the James Franck Institute, which is an interdisciplinary physics and chemistry institute focused on material science in the 1990s. And then I was dean of physical sciences for 8 years at the University of Chicago, and now president. So I've moved through different types of leadership roles. And you will always be people will always joke about going over to the dark side. The idea that the true faculty who decide to go into a dean or a president type of position, they've given up their core values and they've gone over the dark side. Ignore all of that. I really think I don't feel a totally different person from when I was just a faculty member. I still feel connected, and I think there is a lot of interesting work that I can do in a administrative role as well as in a faculty role. So think about your own challenges and directions you might move in those areas. So just in closing then, I would encourage all of you to think intentionally about your plans, about things you might do in the future. Think about ways in which research, teaching, public service, communication, leadership roles might be part of your career at different stages. And also, the last thing to say is be open to serendipity, be open to surprising new things, changes that might come up that might push you in some exciting new directions as well. So thanks very much. Okay.
Well, thank you very much for that. One of the remarkable aspects of this country, of course, is denial of climate change. And a case could be made that universities are certainly culpable in this, because you've probably seen these interviews of graduates leaving on commencement morning and being confronted by everyone from Jay Leno to Joe Handelsman, and ask questions like, why are there seasons, where do these leaves come from? And of course, Jay Leno started at Harvard, so I can pick on myself. And he discovered that only 20% of Harvard graduates knew why there were seasons.
Why we have seasons, yes,
And-
exactly, right.
And most of them thought that the organic material came up through the trunk and formed leaves. And it gets worse from there. So because of this unique group, it seems to me, and particularly with your experience, a lot of this fault lies in the teaching of physical sciences. And if we look at our life sciences colleagues, I mean, Steve Leopard's discussion this morning demonstrated how thoroughly the life sciences have adopted societal responsibility, not only in their teaching, but in the execution of the research that they do. So what do you believe we should do in the physical sciences to step up and take this kind of responsibility? Because in many cases, 20–25% of college graduates, of which there are 2 million each year, don't have the information to know how to vote.
Well, that's a good and big question. First of all, I don't think we should be too critical of ourselves. I think that each of us is trying hard with our own environments. I do think that we should think structurally about our institutions and about what our students graduate with. It's always a hard argument to say we should have more requirements, because freedom is part of the value of a United States education, is that there's a lot of freedom to move around and take different courses from different areas. But it is a concern when people graduate without knowing this. But I would say this is not something that we can fix at the college and university level. I think this is something that really needs to go back to schools. And so it's not that I'm trying to push the problem off on a different area. But it seems to me that understanding things like the seasons, that's something that you shouldn't be graduating from high school without knowing that, let alone college. The trouble is that by the time you get to college, you tend to be getting specialized. And so if you're studying history or whatever it is, no reason you should pick up that knowledge that you should have graduated from high school with. So I would say part of it is the entire way in which, as a society, we're structured, and the way in which we are focusing on teaching to the test and teaching rudimentary skills which are very testable, but which don't really correspond to deep understanding. Some of that's happened in K through 12 education, and it's happening increasingly in higher education. So I think getting students to think about big problems in the world should be starting as kindergartners, and it does happen. They play, they enjoy, and then somewhere through school they start to think, oh, this is something I have to be tested on, it must be boring, and so forth. So I think we need to think about our entire educational system to deal with the type of issue that you're raising. But it's a very good point.
David, that was very nice. Actually, just a comment, and because I had a different question, but a comment on what you just said. I'm convinced that every child is a born scientist.
Absolutely. Yeah.
And it gets, well, beaten is too strong a word,
Right,
but
I agree.
suppressed,
Yeah.
In elementary school often, because the elementary school teachers often, it's the rare elementary school teacher who is not, dare I say, hostile to science. I mean, unfortunately, there just
Scared
aren't
of science.
enough
Scared and therefore hostile, right?
Yes,
Yeah.
exactly. And so I think it starts then, right?
I agree.
And I agree with you that every high school graduate should know a lot of the basic knowledge that Jim is talking about. So now on to my question, which is, it's interesting because I first took on an administrative leadership role 4 years ago, a little over 4 years ago. And I think that, you're exactly right that you need to think about it in terms of, not service in terms of going to jail, but service in terms of what you can do to contribute in a way that allows you to be, to take a military term, a force multiplier, and enable lots of people to be successful and have a greater impact beyond yourself, which is what you can do as an administrator, potentially. However, so I think all of that is very good. One thing I think that universities don't offer often is what I'll call professional development.
Absolutely.
And it's a big problem because you end up appointing people as directors or chairs of departments or directors of institutes, and you don't magically snap your fingers and become a good manager, right? And so, and in fact, you end up sometimes appointing people who you think, well, they're really good at research and they're really good in this area, and people respect what they've done, and so they should be a leader. But they may not have the management skills that are really needed to be as effective as they could be. So, I don't know. It's not really a question; it's a comment. But
absolutely right.
But it's a huge problem, I think, because if you really want effective leadership, we need to have some means of professional development to learn good management skills.
I agree completely, and American Chemical Society has done some things in this direction with workshops for new department chairs and so on, which many people don't take advantage of. So I think there's some opportunities out there, and we need to build them and encourage them, because you're absolutely right that success in running a research group does not necessarily translate into a department which might have anywhere from 5 to 30 faculty or whatever it is, plus staff and so on. So those issues we certainly don't typically get prepared for. The same thing happens at each level. When you become a president, it's not as if there's a pathway where you've gone to president school and you graduate and now you're ready to be a president. You learn new things, and so supporting that along the way is really important, as you say. Thanks.
Role models are important at every stage.
Yeah, indeed.
Exactly. Yeah. So I'm intrigued by your charge to the chemists in the audience to think about how we might become as good as the biologists have been at communicating to our graduates how important and fundamental a role chemistry has to play in society, which made me start to think about the typical undergraduate major, right? Chemistry is a pretty unique discipline in that it seems to me that chemistry major is really 5 mini majors combined, right? All of our students have to become experts in subdisciplines that often have very little on the surface in common with one another. And so when you think about where we might do this, the organic chemists will fire back and say, well, I can't teach this stuff. I got way too many reactions to cover. And the physical chemists are like, I have to do thermodynamics on top of quantum mechanics, right? There's no time for all of this. And so the question really becomes, where in the curriculum can we do this? And I was intrigued by your comments about your textbook development for general chemistry, right? I've heard many general chemistry teachers say, I can't find an appropriate textbook for this course. I've never heard a textbook author say, when it finally became time to teach the course, I decided not to go through my own textbook, right?
Exactly right.
And spin it a completely different way. Is this not the place where we can all agree that perhaps we could write a year-long curriculum that covers all the critical areas of chemistry we care about, but that leaves students with an absolutely fundamental understanding of how important everything they are about to learn more in depth is to a properly functioning society. I guess what I'm saying is, do we need to do it the way textbooks have been doing it for so long, or can't we just adopt your idea, right, and go forward with that?
Well, I think there's a lot of exciting directions we could go, and which might be built around new textbooks which have different approaches, but they could just be bringing faculty together to teach the subject in different ways. And actually, I mentioned that group of young Turks that was trying to redo our curriculum. Part of our goal was to say too much of general chemistry, of the whole first year of chemistry, is sort of mini physical chemistry. And where is the organic and inorganic and other aspects of chemistry? Can't we make our first-year course broader so that it connects to all the exciting areas of chemistry, rather than just being something that the physical chemists do when students are not quite ready to do real physical chemistry? So we were exactly talking about that some years ago. So I think there's a lot of new things we could do with chemistry. Chemistry is the central science, and I think chemistry should be right at the middle of all of the conversations about real issues in society, and to bring those into a general course, introductory course, is exactly the exciting opportunity that all of us have. Yeah.
So I'm the editor of Journal of Chemical Education, and have actually gone back and read things back to the 20s when it first started. And in the first volume, people actually talked about exactly these issues. And so that's good news and bad news, of course, as you realize, because, what have we done? And so I think the fact that a lot of people in this room don't even know what goes on in their general chemistry program is something that's a take-home message. Go take a look and get scared and do something about it, please. Thank you.
Good. Well, thanks for the observation. I do think maybe there's nothing new under the sun, but I think the effort to rethink things is really exciting. So even though we may be discovering something that people also talked about 50 years ago, I think we can change things, shake things up, and I'd encourage you to do some of that on your own campuses. Good. Okay, thank you.